Hey guys, how's everything going today? Early returns. I'm looking at how you made out on yesterday's factoring. You did a great job with the monomials. Now we're going to go on to the next phase, which you'll see posted in a minute. Let's get started. Are you ready to go? Here we go. Okay, so the best way to start is to look at what a perfect square is. And here's a list. Now I'm going to attach this to the assignment for tomorrow, and really should, if you don't know these already, print them out. It would be helpful. But you can see on the left the list of perfect squares: 1, 4, 9, 16, 25. And you can see on the right that those come from multiplying or squaring each counting number. So really through 12, you should know those because you've learned all the multiplication tables since you were probably in third grade. So you should know that 144, as an example, is 12 times 12, and 121 is 11 times 11. Then I would say the next ones up to 15, you should commit those to memory as well. So 13 squared is 169, 14 squared is 196, 15 squared is 225, and then maybe from there, if we back this up, you look at the tens and maybe even 15s. Well, we did 15, right? 225. So 20 squared would be 400, 30 squared would be 900, 50 squared would be 2500, and like that. But anyway, I'll try to include this list in your assignment, like a link to this list. So if you notice that the first and third term of the trinomial that you're trying to factor, if both of those are a perfect square, you can just fill in the blanks. Watch how easy this is. So what gives me x squared is x and x, right? And what gives me 49, because you know that's a perfect square, is 7 and 7. And since both of these are pluses, we do that and that. And then you see that these are the same. So I finish it off that way. Wow, how easy is that, right? So that's why these are special. Now let's change the middle sign and see how that affects things. Well, again, the first term is a perfect square because we would have x times x. So anytime the exponent is even, we know that we have two factors that we can multiply together and get that x squared. The product would be x squared. 16, of course, is 4 times 4. So let's fill this in. X times x gives me x squared. 4 times 4 gives me 16. But the middle term is minus this time. So now I go minus, minus. And notice that these two are the same. So ultimately, there is my answer. That's my factor.
Beautiful ways. I want to share a couple of them with you because they're pretty cool, very important, and we'll see them throughout our journey through math. So first of all, let's just take a look at the trinomial that is a squared plus 2ab plus b squared. All right, now how would you possibly factor that? Well, when we try to actually factor it by grouping, what we see is the two groups are in fact identical. Let's check it out together. A times a squared. Outer terms, an ab. Inner terms, another ab. That's 2ab plus b times b squared. But look, since this thing is the same as itself, I just have that thing squared. This is a perfect square trinomial. What about this? Can you guess what this would be? Well, actually, if you think about it, we can figure it out because it looks very similar to the previous one. I have to think of two numbers whose product is b squared, and yet when I combine them with the a's, I get negative. So what would it be? The sign would have to be what? Both the same sign, and they'd have to be negative signs. And that's right. We get a minus b times a minus b. A times a squared. Outer term, negative AB. Inner term, negative AB. Net result, negative 2AB. Negative B times negative B is positive B squared. So there we can see that we have A minus B all squared. These are really important and fun. Let's take a look at some examples where you can see this happening in action. Let's try to factor x squared plus 8x plus 16. What I notice immediately is that I can write that in this form. Now check it out. This is actually x times x. I can write this term as 2 times x times 4. And I can write the 16 as 4 times 4. And so you can see the perfect square, and 2 times the product of the numbers themselves. And so immediately I see this equals x plus 4 times x plus 4, or alternatively and equivalently, x plus 4 quantity squared. So when you see something squared, 2 perfect squares, and in between it's 2 times the x times the 4, the numbers themselves, product, then you know you've got a perfect square. Let's try another example together, just to give you a sense of how you can ride the wave of perfect squares. Take a look at this. 9y squared minus 6y plus 1. Again, I can write this as 9y squared is the same thing as 3y times 3y. I can write the 1 as 1 times 1. That's a perfect square. And what about the thing in the middle? I can write that as negative 2 times what? 3y times 1. 3y times 1. Therefore, this tells me immediately I can write this as 3y minus 1 all squared. So sometimes these things can be factored really, really quickly once you realize that, in fact, you're looking at a perfect square. Okay, you asked for it, you got it. One last one. Let's see if this is a perfect square. X times x, here I see 5 times 5. The question is, do I see in the middle 2 times 5 times x? Well, no, I'm actually seeing 6 times x to get me to be 12, and 6x does not equal 5x, which is what we need to make this a perfect square. This is not a perfect square. Sadly, this is not a perfect square.
Okay, next one we're going to work on slightly different. You can see there's a factor of 5 in each of these 3 coefficients. So we're going to single out the monomial like we did yesterday. There's an x, and the lowest x, exponent-wise, is this one that's x to the first. So we start with that. Now, as we worked on yesterday, 5x into 5x to the third. So this number divided, or this term divided by this term, would give us x squared. This term divided by this term would give us 10x. This term divided by this term would give us that. So now we have a trinomial to work with. We're not done yet, though. So you rewrite the monomial, and now you go like this. Okay, so we know that this is a perfect square and this is a perfect square. So we just enter x and 5 and 5. Everybody see that? And this dictates what our sign is going to be. And now, since these are the same, I can rewrite it that way. And that is the factorization of that trinomial. How about that? Now, this kind of goes back to Friday's lesson where we have a trinomial, okay? We do have a perfect square on each side, but we need 2 factors of 400 that are going to equal out to 40 when we add them together. So since this is a perfect square, let's take a look. 20x Oop. And 20x, that was weak. And when we multiply those two together, we get 400x squared. So we're doing good. 1 is also a perfect square because we have 1 and 1. And then the signs dictate that we go that way. And then you'll notice right away, obviously, that both of these are the same. So I rewrite this and make it squared. Okay, so that kind of finishes or concludes the first half of 21.3. So tomorrow we'll look at the difference of two squares. We'll have a negative sign in between it, but it would be good for you to really peruse that page I'm going to give you and try to memorize or write down or keep handy the perfect squares so that this factoring becomes a little more easy for you. All right, now I'm going to put together a sheet and have 5 or 6 problems for you via Google Forms. Good luck. Nobody is getting on my conference call, so tomorrow I will probably put up a Zoom call again at 10. And if you'd like some help on this, I'd be glad to provide that, okay? Or get in touch with me individually, either through email or let me know when you're available. And as long as it's before like 1:30 or so, I'd be glad to go on and give you a little help via call. I'd like to see everybody anyway. Notice who that is over my shoulder. A signed picture from Mike Trout. Wow.